except when I am. Good enough. Okay, so last time we started talking about molecular orbital theory. We're gonna.
Between 1s and 1s.
Yep, we were there, but we are gonna review of MO theory. Before we keep going, we're gonna talk about molecules. Okay, let's refresh ourselves on the rules so we can build good MO diagrams. Give me a rule.
AOs in is equal to MOs in.
Yep, and AOs stands for what?
Orbitals in.
Yep. Yep. Give me another rule. Yep, AOs overlap. Sometimes they'll say hybridize to make molecular orbitals. Give me another thing. Somebody other than Joe. Mm-hmm. Yep. So the new MOs that are made have, if they're bonding combinations, they have to be lower in energy than the atomic orbitals. Somebody other than Lily and Joe, give me one. Yep. Best when close in energy. Aiden, give me something.
Bonding MOs are lower.
Yep, already got one.
Antibonding MOs are higher.
Yep. Anti-bonding.
What's the sixth one? Yeah, what's the sixth one?
Nope, I'm opening it back up to the students. 6.
Off-ball.
Yep, got to follow the off-bow principle. An off-bow principle is made up of what two rules?
Ground state structures must follow Hund's rule and Qualitative.
Hund's rule, Pauli exclusion principle. Yep, Hund's rule, how do we fill electrons? Yep, exclusion principle, what's that one state?
Can't have the same
Opposite spins, can't have same quantum numbers. Yep, we're missing one more though, a really important one. Yeah, symmetry. AOs are only permitted to mix if they have correct symmetry. Sorry, we're going to say can mix. Only if proper symmetry. So there's just some symmetry constraints that we're stuck with. So some functions just can't overlap because of that symmetry. I'm going to open the window. I'm going to freeze you out, Joe, sorry. Okay, these rules you should know by heart. If you don't, like, I don't care that you know, like, the exact wording of the rules, but you should inherently understand those, okay? After we reviewed the basics of MO theory, what did we start talking about next? Yep, types of overlap. And that's incredibly important too, because it will help us draw our molecular orbital diagrams. Types of orbital overlap. Then we had our cool little table here, where we had our system. Oh, sorry, stuck in thermodynamics from my last class. Symbol, and then number of regions of overlap. Okay, we had 4 symbols. What were those 4 symbols?
N sigma pi over.
Yep. And then we had the regions of overlap. So N is for what type of orbital overlap? Yep, non-bonding, 0. Sigma's for sigma bonds. Regions of overlap there? Yep. Pi, 2, and then we have a jump. Yep. Okay. And then we started considering, as we let these these atomic orbitals overlap, we drew kind of those pictures of them very localized, and then we showed what happened when they hybridize and become more delocalized. But if I drew an s orbital like that, is that really representative of what that function looks like? No. It might be a region of high probability, but where does the probability cloud go for this thing? It's everywhere. It's technically, it can approach 0 and be really close to 0, but it's not necessarily 0. So it extends out really, really far. But we draw them this way because this is easier to understand than doing like that. Yeah. That's a good one. Yeah, at least one of my electrons is on the board somewhere. If the universe is my board. Okay, sorry, that was a good one. Then we looked at the overlap between two S functions, between 1s and a 1s. Here we said the two are in phase. This is before they mix and hybridize. What are they going to look like afterwards? Yeah. And the kind of, I should have drawn them closer, but they overlap in how many regions? 1. So what type of orbital is this? Yep, it's a sigma bonding. Then we could switch the sign of the wave functions. So we show this scribble as a way to show positive and negative. It's really preference. This one could be negative or positive, but just that there's a sign change. How's this one going to look like?
Yeah.
Yep.
No,
Big node. And what type of overlap is this? Yep. Yep, anti-bonding. And we denote anti-bonding with a little star here. Okay. There is a node where the probability is 0 in between. Again, I'm drawing it like there's nothing really here. Most of it, it's more likely to be on the edges, but there is still some probability here. Okay, let's keep moving. Let's look at 2p's. And that table I just erased, you want to keep that in mind. Example, overlap between a 2s and a 2p. Oh, we're mixing stuff. Never mind. We're not going to do 2p's. We're going to do 2s and a 2p. Okay. S orbitals are spherical. What do p orbitals look like? Yep. Okay. So we have two possibilities here. What's something I'm neglecting on that p orbital?
which one it
Like
is?
shaking it in, or
Right.
which one is like
Right. So when you think of a p orbital, I'm going to draw one over here. Yeah, I didn't indicate its orientation. Let's just call it x. And say this is the x-axis that it's along. P orbitals, if you look at their wave functions, they have a sign change across a point, right? So I'm neglecting that on here. I'm going to keep the s orbitals as positive. I could draw one like this. I could draw one like that, where I've changed the sign. I could have changed the sign of the s orbital, but who cares? It's the same thing, right? Yeah, just depends. It's like all positrons we say are positively charged, but if we were in some alternative universe where we define them as to be negative, then all of our electrons would be positive, all our neutrons would be negative. It's just preference. It's weird. It's weird to think about it that way.
It was a vector thing where if you multiply one and then the other, it's not the other way around.
Yeah, I mean, no, but yeah. Okay, we're going to let these things mix. How many regions of overlap do we have for the top guy? 1. Okay, so what type of orbital are we going to get there? Yeah, going to get in sigma MO. What's it going to look like?
It's gonna look like P orbital, but like big, and then the tail.
Yeah. So it'll be weep, a little bit over there, and like that. And what do I got to do to that tail, Joe? Yeah. There we go. What type? We said it's sigma. Yep, sigma bonding. That's a sigma. Okay. Now this guy. How's that one going to look?
Like the little
And then
Okay. How am I going to shade this thing, given my initial picture?
the little tiny one on the
Yeah. Perfect. And what type of overlap is that? How many regions? Well, it is 0 after they... Yeah, this guy's a sigma star. Okay. All right. Let's keep moving on. So we could have an overlap of sigma between a 2s and a 2p. Could be different p orbitals too. Could be a 3p. Could be a 1s. There's differences there. Let's consider the overlap between a 2p and another 2p. Okay. Now, those are our points, just like we had here. We could orient p orbitals that way. Okay, how do you want to shade this top one? Which lobe do we want to shade in for the first atom? Okay, you want to do the left one? We can do that. Okay, for this one, which one do you want to shade? Right one? Okay.
Let's keep the pattern. The first one is
If you want to, it depends on what pattern you want. You want phases to be a pattern, or you want bonding. I actually don't like the bonding orbital on top because that implies it's higher in energy, but we're there. Don't think of it that way.
Well, we don't have the bar as energy.
Yeah, see, yeah, there you go. No axis. Yeah, there we go. We're putting energy like this. We're good. We're good. We're fine. All right. This one, everything's perfect. How do you want to shade this guy in? Left or right? Okay.
No, Joe.
It's done. We did it. Okay.
Disgusting. I'm sorry.
Then how do we, I want to shade this one like this. It doesn't matter. I love it. The obsessive compulsive nature of people. It's like every person is slightly different, but aggravates them more. It's like my household. It's fantastic. Okay. These are two p orbitals aligned in the same axis. How many p orbitals do we have per energy level? Yep. So we're going to have a set that points this way, right? Yep. Aiden, you're already doing it. Where are the other ones going to point? Yep, we're going to have some that point out directly at us. And what's the other one, Lily? Yeah, up and down. Okay, the up and down ones are way easier to draw. We realize that we have two of those. Yeah, I don't mind it. I can see it. Now, the other unfortunate thing is we draw these really localized orbitals, but again, are they really like this? No, they extend out way further. I am going to draw a line here so we don't get confused. If I draw an orange, is that okay? Kind of separate everything, because I'm kind of getting it all mixed up a little too much. Okay. And again, we have one set that'll be like this, two sets that will be like this. How do we want to shade the top one? Black on the bottom. Okay. What about on this guy? Black on the top. Okay. What about here? That's okay.
No, I broke it.
You did break it. That's okay.
I'm sorry, guys.
Okay. What about here? Bottom. What about, and then we want that one. There we go.
No.
Yeah. We're just breaking different types of order here. Okay, that first one. Tell me what's going to happen with the overlap. It will be a sigma bond, sigma bonding.
It's gonna do two little tiny things on the outside and then a big one on the inside.
Yep. Yeah.
Yeah, candy.
I see a cow's eyes. This is the cow's forehead.
I like that so much more now.
Now, when we draw the other one, it'll look like the nose. You'll see it in a second.
Let's name it cheese grater.
Okay.
Oh, that's fine.
Cheese. Okay, how's this one gonna look? Yeah, be like that. Then a little blip. Little blip. How am I gonna shade this thing?
The right side.
Yep, what about in this one? Yep. And what type of overlap is this? Yep. See? And that's the cow's nose. These are the sides of its face. I don't know. I didn't see it, and then one year I taught inorganic, and they were like, the cow, and I'm like, the cow, and then they kept on drawing cows, and now when I look at this, I just see a cow's face. Yeah.
It does kind of sound like
Their obsession with that. That and the referral of alpha is Jesus fish,
Yes.
and psi is Triton.
Alpha is 100%.
Wait, was that the same group?
That was the same group. Yep, it was Maddie, Tara, Josh, and John. Anyways, okay, this next one. Joe, what color can I color with so you can see overlap here?
You can use green or red. You just can't.
Can I use yellow here?
Yeah, no, you just can't use them at the same time.
Okay. Now, we're going to show overlap. We have to keep in mind, remember, that I'm just drawing localized AOs, but they're diffuse, right? So we're going to show overlap along here and here. How many regions are we talking about? Talking about 2. So what type of symbol are we going to give this thing? It's pi. It's going to be pi bonds. Okay. Let's consider what happens with the overlap and what it looks like. So again, these are the atom centers. Okay, which one do you want to do first, the top or the bottom one? Top one? Okay. Overlap with the top lobes, constructive or destructive? Yep, so they're going to kind of cancel each other out. They'll push away a little bit. Let's color the lobes properly. What about the bottom 2 lobes? Yep, also destructive. How should I color these? Yes. What type of orbital is this? Yep, this is a pi star. Anti-bonding, nodes, nodes. This guy, the top lobes, are we going to have constructive or destructive? Yep. Sorry. I drew that not how I like it. Still don't like it. Well, whatever. It is what it is. It should be symmetrical. Why can't I do this today?
It's because you started on one side, not on the
Yeah, I know. There we go. Better. Okay. There we go.
Chicago.
See.
It's the beans.
Cow lips. I see a smiley face with a guy wearing one of those, what are they? Beret.
Oh, I can't see it. And is it weird that it kind of reminds me of Dr. P?
No, that is perfect. Dr. P, Pi Orbital workout, Jimmy Pi. It's all coming together right now. All right, overlap. We good here? Do we need a star? No. We're good. Okay. We can have other pi orbital overlap happen. I'm going to leave that for your guys' daily problem to figure out some of that stuff.
Like EXs versus QIs.
You'll see.
I think he's going to ask you like
No, that we are going to talk about delta overlap because delta overlap is somewhat hard to see. So the next one we're going to talk about, 2dxy's. So you also need to know what the atomic orbitals look like for the D system. What do the D orbitals look like?
Donuts.
Yep, some clovers, butterflies. So there's like dxz, we'll call it, because this is the plane of the board. It'll look like that. How would you want to shade this thing, though? I saw your hand signals. Can you? Yeah, like that.
And when you're drawing that, are you drawing that in terms of the board? Or
I'm drawing it flat with the board. Okay, is that the? So some of them have the shapes. There's one that has a unique shape.
It's the one. It's probably a teardrop and it's got like a donut.
Yep, and there's the donut around the middle. Now, where would I shade?
Would be either the donut.
Yep, either the donut or the lobes. Okay, so these are the shapes of those, right? How many of them have this sort of shape?
like all.
Like all of them except the. Oh no, isn't
Mhm.
there two of them that don't? Because isn't there another one?
Oh,
It's
It's rotated a little bit. Yep, there are 5 of them. So
the Z is one, and then the other 4.
yeah, kind of like this. They do have different orientations. Though.
Is the one that's like it's like X squared minus Y squared.
Yeah.
Is that one not?
That one is aligned along the axes.
Oh, it's just tilted.
Yep.
Okay.
Also, is
Mhm.
this easy squared?
Oh, sorry, there should be a dz squared. There we go. Thank you. That would have been bad. Okay. Now, we can't... This is one of the better orbitals to try and draw this way. If this is the XZ plane in the plane of the board, we're going to draw XY. Where is XY going to point? Yep, so we're calling the plane of the board the XZ plane. Where will the DXY point? Yeah, out of the board. We're going to try to show it at an angle. So this one is meant to be behind that guy. I'm going to try to shade it, and maybe it will help out a bit. Like that. Yeah, it's thinking genetics. Terrible. Not in this class.
We have alleles and alleles. No
Yeah.
difference.
And now let's say we have another one lined up like this. I don't know what that word means, but good. Yep. Okay, Joe, what two colors can you differentiate? If I have yellow and red,
Yellow and blue, yellow and red.
yellow and blue.
You just can't use the green and red together. That's the only.
So these guys are stacked like this, like edge to edge, okay? We're going to show positive overlap with the stuff behind the board in yellow and stuff with positive overlap coming out of the board with blue. Okay. Positive overlap coming out of the board. This one, does it have any positive overlap? Yeah, it does.
Oh, I was thinking.
Along there. Any other ones coming out? Yep. Overlap there. Now let's go for the back. Yeah, same thing. I can't show the overlap going all the way through. This is not a triple bonds. Well, it can be comprised. That's a hard thing. We're not going to talk about that yet. How many regions of overlap do we have? We have 4 regions of overlap. What type of bond is this? It's a delta bond. Okay. Now, let's try to draw this out. We can have 2, this one is a positive combination, right? Meaning constructive interference. How many lobes do I need to draw?
4.
Yep. So let's try to do it in color, like that. And we got one behind it, which is shaded. Now this one, and then there's one behind it. Two hot dogs. Where should I shade the bottom one? The one in the front or the one in the back? Yep. What type of overlap is this? Given how many regions? Yep. Yep, this is a delta bond. Okay.
Yeah, I just cannot draw that.
It's hard. What I would suggest to do is look up pictures of it. There's way better pictures than we can draw of this.
I should have brought my thing from the organic.
Like, I understand what I'm looking at.
I'm
just trying to draw in the notebook. I can't do it.
That's all that matters right now, is that you understand what you're drawing. Okay. Everybody feel comfortable with these ideas? Okay. We're going to utilize them to build our MO diagrams, which are going to tell us about the electronic structure of molecules. We're going to start with a simple one, H2, because we're going to utilize H2 a lot. Then we'll go to some diatomics. After we go through these systems, what we will do next is start talking about solids and lining things up in infinite chains and seeing how this starts to change.
Is that next class or is that still?
We will see. We probably, it might hit next class. Might. Yes. Yep, we're going to do hetero and homoatomic. I only care that you have a good idea of what they look like. I don't care that they're exactly right, because you only know how right they are based upon prior experience, which you guys have very limited amounts, or quantum chemical calculations. So let's draw the MO diagram. or H2? We indicate our axis with which way energy is pointing because that's important. If we don't do that, then we could end up at the opposite result like we did last time. We need to indicate our atomic orbitals. So we usually have 3 columns here. First column is for whatever atom we're going to have overlap with the second atom, which is in column 3. And then we indicate our molecule. A lot of times I like to draw this lower just so we can see, but it doesn't really mean anything. It's just to separate things out. Okay, now what I want you guys to do, what is the electron configuration of a hydrogen atom? S1. Okay, gave that away. How many atomic orbitals do we need to draw? Yep, 1 for each. I usually write the symbols like that. Okay, how many electrons are occupying? 1. Very good. Doesn't matter if we draw them spin up or spin down. I'm learning a lot about something called parahydrogen, where you can actually have the nuclear spins either aligned or anti-aligned, which is really weird. We're not talking about nuclear spins, we're talking about electronic spins here though. Okay, s orbitals. These guys, are they close to one another in energy? Yeah, they're the exact same energy. Well, they should have been. I drew them kind of crooked, my bad. I'm referring to spins. Yep. Okay. What about their symmetry? Same symmetry. Is that good for overlap or bad? Good. Okay. Tell me what's going to happen here as we let these atoms approach one another. So that? Yes. How do they make a sigma bond? They have overlap? No, it's okay. Keep going. Yeah, they have overlap. Okay. So there's a formation of how many MOs?
Well, 2.
Yep. There's one that's lower. There's one that's higher. Okay. I'm showing dashes here to indicate that these AOs have contributions, bless you, to these new MOs. What do you notice about the distance between this lower energy one compared to the AOs and this one's closer? Yep. That is correct. A lot of textbooks you will see will draw it where this energy is not higher in energy, which is not good.
Wait, they don't draw it as higher?
They will draw them equally spaced here, which is incorrect. Okay. So now we have these 2 new MOs. We can label them in a little bit, but where are the electrons going to go? Yep, they go to the lowest energy state. Happy there. Okay, when we think about the MOs, we can label them with our symbols that we utilized back when we were talking about Huckel theory. If we consider that one, we have s orbitals that look like this, but then we permit them to overlap. What are we going to get out? Yep, oval. What type of bond is this? Sigma. So we might write sigma instead of that psi 1. Okay, the other one, psi 2. This time, we moved them out of phase with one another. They're destructive. What's that one going to look like? Yep. And what type of overlap is that? Yep, sigma star. This one looks more like a cow to me now. There's the cow nose, ear, ear, eye.
Oh, I see. Yeah.
Yep.
I see a pig, actually.
Oh, because these ones is just
Okay.
screwed with a hat.
So now, looking at this, was this very complex? Sometimes you'll see the representation of this, like that, where you'll have orbitals listed this way. And even though they don't show the hybridization or the mixing, that's really what they mean. Everybody feel comfortable with this one. We're going to hit this a lot, okay? Especially when we go to talk about band structures, because it is the simplest case with the band structures. Yeah, there's a lot more there. Yeah, the semiconductor industry, it's a big one. One of my conference buddies is working for Samsung right now as a consultant, and he says it's incredibly interesting. They'll go into meetings and they'll have to get rid of all the electronics. They have to check them over for bugs and different things. Random access memory, RAM, they just figured out how it actually works from a chemical level, which is crazy to think about. We've been using this stuff for a long time. We haven't known how its behavior is, and he determined it. I'm sorry, what was that? No, like meaning like making sure no one has any recording devices or anything on them to sell proprietary information, because there's a lot of fight for that. Yep. Let's draw the MO diagram. For O2. Yep, that's one I always ask. No. I would not make you do NO.
That one is diabolical. She showed me how to do it, and I was like, that's crazy. Well, that's different, right? One's Gen Chem, the other will have whole forms.
It should be. All right, oxygen. There we go. Tell me the electron configuration for oxygen. Yep. Okay. Most of the time, do we care about the core electrons? Which ones are the core? Yep. Here's our valence. Let's just consider the valence electrons. Okay, how many orbitals or atomic orbitals should I draw for each oxygen? Yep. I should have a 2s here, and I'm going to make it higher up. You probably want like half of a page for this, by the way.
Me drawing really small.
I was gonna say, my hydrogen was like that.
What about the P's? 1, 2, 3. Yep. We want to mimic the same thing over here. Okay. We can fill this guy. How should I fill these p orbitals?
You should use
Oh, you have to put one in each.
and then you gotta find one that's just not gonna be happy.
Yep. Perfect. Okay, let's use our intuition to try and predict what new molecular orbitals are going to come out. How many MOs are we going to have in total? How many AOs are going in?
Oh,
8. So we should have 8 MOs out using our minimal basis functions. Okay, next. We're going to assume orbitals of similar energy are going to mix most efficiently. what's going to happen with the s orbitals?
Two orbitals.
Mhm.
One lower and higher, you're gonna have two electrons.
Yep. And sigma star, right? No, I'm just bad at drawing.
Real.
Should be in the center. I didn't do a very good job.
Will the sigma be closer than the other one, or how would that go?
The sigma star should be higher. But
Should be further away.
yeah, it's really not super. I mean, it's of importance to make note, but for what we're doing right now, not super important. P orbitals. We have a bunch of different combinations that can happen there. What's going to happen? Mm-hmm. Yep, I'm going to draw the sigma orbitals in yellow. Here is the sigma. What about the sigma star? Yep. Okay, what about the other 4 atomic orbitals? Yeah. So if we think back to the AOs that we drew, now what can you say about their energy? So I got 1 pi.
They're the same.
Yep, they're the same, they're degenerate. And they're above, they're higher in energy than the sigma, is that right?
It depends.
It does depend. In this case, it is correct. Now, what about the pi star?
That's going to be above the sigma, right?
No, it's gonna be lower.
Yeah, it's going to be lower. Okay. Let's fill electrons. We got what? How many left? 8? 4, 5, 6. What about the last 2? Yep. We will get to bond orders in a little bit. It is too. Good work. What's unique about this system?
Paramagnetic.
It's paramagnetic. Yep. It's a diradical, some people consider it. It will respond to an external magnetic field that's actually attracted. It's incredibly weird that we owe our existence of life to this magnetically active molecule that we breathe daily. The system, things don't really like being magnets. They're just stuck being that way. It's partly why oxygen is so incredibly reactive is it really doesn't want to be this way. It really wants to get out of it if it can. Okay. Any questions about this one? Do you feel like you understand why this sort of splitting happens?
Like, isn't like ice.
Yep, why we have these pi orbitals here, why we have these sigma orbitals here. Like because of the p overlap on how these things could be organized? Or not really? Or are you just memorizing this? Okay, that's what we don't want. Okay, can I have p orbital overlap this way? Oh, I actually got models. I'm gonna go get my models. So we got overlap this way, right? We got overlap in the plane of the board, like that. And we got coming out of the board. And then there's stuff in the back. So it's happening in all of those directions. Let me go get my physical models, which I bought, and you can check them out. I'll be right back. Okay. So these models show a good example of a single pi interaction. And these ones show 2 pi interactions. So I want you to check them out, hold them. This guy's benzene. Benzene shows a unique property where you have a lot of delocalization in that ring. But you can see the overlap that way. So do you get more by looking at that, what's going on here? Like that we have overlap. So can I actually steal that model? Okay. So if we're drawing this picture, there's got to be a combination. So we have the sigma bond and the gray, right? We could have bonding and anti-bonding. Then we have the orbitals coming out. The ones that are up and down, they can each have a bonding and an anti-bonding combination, right? Yep. So that means like bonding combination here. The other one has to be symmetrically equivalent, so they got to be the same energy. Does that make sense?
Yeah. So
Stare at it for a little bit. Yeah.
So currently, because in the they're the same color in the X plane and then in the Y plane coming out of it.
Sure.
They're the same color. But on that one, on this one, they're not. They're like.
Yes, that's to show differences.
Are they like bonded?
That is actually using a different electron model. It's not using MO theory. It's using valence bond theory, which is like weak MO theory.
So
okay? But no, valence bond theory is not wrong. So in some cases, it's incomplete. But really, this is a model. We're trying to just understand things. There are times where the model is incorrect, and there are times where it represents reality better. It's a model. It's like, what is a single bond? It's an idea. Okay? So what we're showing there, I guess, can you ask your question a little different?
So you know how we were talking about the shaded regions?
Yes.
Right?
Oh, okay. So
will
this
be shaded, this is unshaded.
Yeah.
This is unshaded.
Yep, that could be. It could be that way.
So in this case, because the shading and the unshaded are opposite.
They're not alternating like on the board.
Yeah, they're not.
Right.
This is
It's not
not.
like it'll be like plus
This-
minus plus minus.
Right. Is only showing the bonding combinations. Okay. It's not showing the anti-bonding where they would have, like, what I would have to do is switch a purple and a pink, and then there wouldn't be a bond in between. Does that make sense?
So wait, why is it that the pies have to be equal and the sigmas don't?
They're bound by symmetry. The other thing is the quality of overlap that they have. The sigma bonds have a higher quality of overlap, meaning there's more overlap between them. that drives the bonding combination down in energy and the anti-bonding combination up in energy. So the more overlap you have, it's called dispersion. You increase that dispersion.
Right, so
Okay?
it's going to increase that
Yep.
sigma star more than it's going to increase.
Right. And then this pi system here, there's not as much overlap as you can sort of see in that sigma region. So the dispersion, that splitting, is less.
Oh yeah, it makes sense to me why the pi is increasing.
Yeah.
It's more like the why they're equal. Or are they both unequal? In magnitude of the pi.
Oh, like this should be a little bit higher in energy.
Okay. No, that makes sense.
Okay. Any other questions? All right, good questions. I want you thinking about this. Next time, we're probably just going to draw heteronuclear atoms and possibly talk about like charge transfer interactions between things. Okay?
What is the MO?